This meeting is being recorded.
Let's take a look at sample exercise 10 from chapter 15 on chemical equilibrium. So the next example here on our worksheet mentions that we have a closed system and we're given some initial values. So our first value given is this 1.000 to the negative third molar for H2 gas. Then we're given another initial concentration. This time it's 2.0 to the negative third for I2. Notice they're both at the same temperature. This reaction is allowed to reach equilibrium. So two reactants are charged in some closed vessel. Then we see that an equilibrium concentration for HI is reached here, right? So this is molar. So 1.87 to the negative third molar. And we see here the reaction. I've exaggerated the spacing a little so we can try to line this up with this table that we see below. So the table below is called an ICE table. So we're going to look at here the initial values, what change occurs to reach equilibrium, and then the values at equilibrium. So you can see where the ICE comes from. So down here we have a list of some of the information, some of the things that we can infer from what we're told. So first here, our concentration of HI increases from 0 to 1.87 to the negative third. So we know that initially we had none, so we're going to put a 0 here. And then we know that at equilibrium, it's going to be 1.87 times 10 to the negative third. So let's see what else we know here. So the stoichiometry of this reaction would tell us that both of these values, the two reactants, since they have a 1 coefficient, they would decrease by half as much. So if we have assigned a variable x for these, say, we could say that if each of these go down by x, half of that would be, half of the value of HI would be x, so HI must be an addition or change of plus 2x. So since these are 1 to 1 and this is a 2 coefficient, you can see we can just easily carry that down and subtract minus 1x for H2 and I2, and then we have plus 2x. So we also can plug in our initial concentrations up top here. So that was given above. So we have 1.000 to the negative third here, and then we have 2.000 to the negative third here. All right, so we're given our initial values, our change, and then we can just add these columns or rows together and see that we end up with 1.000 times 10 to the negative third minus x here. And like so, 2.000 times 10 to the negative third minus x over here. So how can we solve for x? We can use these values here and say that 2x must equal 1.87 times 10 to the negative third. So if we divide that by 2, we can see that x would equal 9.35 to the negative 4. Now we can plug in those x values here and here, and we can get our equilibrium value. So let me change colors here so we can see our final values that we can plug in, and then it asks us up top here to solve for Kc. So that's our equilibrium constant. So we're going to get all these equilibrium values down here and then plug them in. So 1 minus x, 1 to the negative third minus that 0.93 to the negative fourth, we get over here 6.5 times 10 to the negative 5. Here, I'm going to get 1.065 times 10 to the negative 3. Remember, that was a larger starting amount. So now I have 1, 2, 3 values at equilibrium. I can plug that over here into my Kc expression. So remember, we're going to have products over reactants raised to their stoichiometric coefficients. So I was given 1.87 times 10 to the negative 3 For my equilibrium concentration, my product HI, I'm going to have to square that. Again, from the balanced chemical equation, it has a coefficient of 2. And then down here, I just solved 6.5 times 10 to the negative fifth. Both of these have coefficients of 1, so we just plug them in as is. This is to the negative 3. So I just square the top, divide by the product of the two values in the denominator, and you should get a value of 51 even here. And I've simplified to just only two sig figs because of that first value.